Access control for shared computing environments, whether that environment is made up of scripts, virtual machines, or containers, is an essential task for any chief security officer. Up to this point, you and Brady's team has spent a fair amount of time working with OpenShift's built-in concepts governing how containerized applications and users on the platform are able to access protected Linux functionality, primarily via security contexts, SCs, and security context constraints, SCCs. Linux is at the kernel of the operating systems like CoreOS, Red Hat Enterprise Linux or RHEL, and a dizzying array of applications and platforms across the industry as a whole. Linux functions and features such as shared file systems, root access, process commands, and their ilk all need to be securely managed in order to prevent a hijacked, breached, or otherwise made insecure container from spreading contagion across other applications that are making use of the same shared Linux kernel operating system. In other words, the protected Linux functionality that we mentioned needs to be safeguarded at all times. How we protect such functionality is made possible via SCs and SCCs. Now that you have a basic degree of familiarity with how applications are deployed to OpenShift, it's an ideal time to explain in detail how exactly an administrator implements SCCs and SCs within an OpenShift environment. And most importantly, understand what it is that makes OpenShift's approach to securing containerized workloads so unique within the marketplace. There are levels of default security that are set out of the box with Linux distributions such as RHEL and CoreOS, and even OpenShift itself. And for the most part, cloud-native applications are able to operate as designed within those constraints. However, there are scenarios often encountered by the CSO teams, such as Brady's, that require a greater level of access or more finely grained permission controls. And in those circumstances, it's beneficial to understand how to tweak existing SCCs and how to define your own if necessary. Mechanically, one can conceptualize security contexts, or SCs, and security context constraints, SCCs, as two key pieces, a key and a lock, that must fit exactly together in order to unlock the protected Linux functionality that's being requested. Imagine an application being deployed by Amy's team that requires access to a core Linux capability such as the kill command. The command itself is not necessarily malicious, as it has innocuous purposes within Amy's application. But given the potential for abuse should an attacker hijack a container with such elevated privileges, it's prudent to limit what users and apps can access the kill command. Amy's team therefore needs to petition the OpenShift and Linux system by submitting a request for permission, if you will, by creating a security context for the application and the pod that's going to run within that specifies exactly which Linux permissions, the kill command in this case, that the app will need to perform its intended duties. You might think of this SC as a proposal document awaiting approval or rejection from the governing body, in this case, the Linux operating system itself. But recall that the SC is only one part, the key, to the lock and key mechanism for unlocking Linux protected functionality. The security context constraints, the SCCs, or the lock, of the Linux kernel ultimately dictate what permissions the cluster will allow applications and containers running on the platform to receive. The permissions being requested by the app's SCs must align with the permissions allowed by the kernel's SCCs in order for the key to turn the lock and open or grant the functionality to the containerized application. An application running on OpenShift can only access the functionality that the container or the pod requests, in other words, what has been requested within the SC, and only if the cluster's SCCs permit those SCs to exist. If the two elements do not agree, the deployment of the container will fail, and the requested functionality will be disallowed. Containers must declare to the cluster, on behalf of the containerized application code that they are tasked with deploying, what functionality and permissions that application requires access to. Recall the deployment manifest YAML file that we were asked to modify earlier in this lab. That manifest, or that declaration, detailed particular permissions that the application required to perform its work. In other words, it contained specific security contexts, SCs, that were needed by the containerized code. The application itself, however, doesn't carry that request to the cluster. Instead, the pod, that container, being deployed by OpenShift relays the SCs and those requests that are embedded within for validation against the list of security context constraints, the SCCs, that are supported by the cluster. Consider the illustration depicted here, where an application and its pods are requesting access to a protected Linux function P2 and P5. Let's say for the sake of example that P2 represents a kill function that Amy's team needed access to, and that the P5 is permissions related to the file system. On the left side, the requesting pod is denied the permissions requested by the developer's custom SC, as they do not match the keyholes, the permitted functions of the cluster's SCC. Only the P7 function, as the SCC is defined, is currently permitted for use. On the right side is a scenario where the cluster administrator on Brady's team have deployed a custom tailored SCC to the OpenShift cluster, which grants access to functions P2, P5, and P7. Amy's application only needs access to the P2 and P5 functions, which are granted by the SCC, and because the P7 function was not requested as part of the SC from Amy, P7 will not be assigned to the pod once deployed. This is in keeping with the philosophy that only protected Linux functions permitted by the SCC be assigned to new pods, and that no permissions beyond what was requested are assigned either. The principle of zero trust and least privilege are adhered to at all times in this scenario. If the application asks for access to disallowed functionality or permissions which are not in alignment with the cluster's SCCs, that request will fail, and in turn that containerized application code and the pod that supports it will not deploy. The deployment fails because Linux has blocked the action as a result of the mismatch between the application's SCs and the cluster's SCCs, a fundamentally important and core concept as to why Red Hat distributions of Linux are inherently more secure compared to other alternatives.